So when I left off a second ago, I was talking about this unifying theory of geology, which is plate tectonics. I've also tried adding a lamp off to my side because I went back and watched that video, and there are all these shadows dancing around everywhere, and it was getting kind of annoying. So hopefully this is better, but we will see. Um, okay, so what I was talking about before was that there, the Earth itself, and the it's really just the outer shell of the Earth, the crust, and just below the crust, is divided up into these series of interlocking pieces, which are called tectonic plates. And it's the movement of those tectonic plates that basically describes or predicts or creates most of the landforms that we see on the surface of the Earth today. Well, one of the things you might wonder about is, first of all, where does the energy come from to cause these enormously heavy chunks of rock to be moving around and crashing into each other? And the answer to that is that it comes from radioactive decay. There is the all matter, all the elements that make up everything that we see around us, everything from hydrogen, helium, lithium, beryllium, all the way up to uranium and so forth. They're all bound together to make up everything that we know and see: our rocks, the air, the water, the book in front of you, the computer, everything, trees. And some of those elements are radioactive, which means they spontaneously break apart. And we refer to that breaking apart as decay. So they spontaneously decay. And atoms are obviously infinitesimally small, but nonetheless, when one breaks apart, sometimes, if it's the right kind of decay, we don't have to worry about those types. But in some cases, when radioactive particles spontaneously decay, they give off a tiny, tiny amount of heat energy. Well, if you've got lots and lots and lots of those over a long period of time, like you have particularly down near the core of the Earth, then that heat begins to build up, and the heat wants to go from, just like when you grab a hot frying pan, it wants to go from the hot frying pan into your hand, not from your hand into the hot frying pan. It wants to go from where it's hotter to where it's cooler. And so that heat is going to be migrating out from the core towards the surface of the Earth. And that heat is what provides the engine that causes the tectonic plates, which are up here, to begin to move around. And the way that works is a little bit controversial, but for the most part, you can think of it sort of like boiling water. The heat warms the rocks rise, they fan out here, generally at the base of the crust, and in so doing, they give off their heat to the crust, and then they sink again and get warmed by the heat near the core, and that makes them less dense and more buoyant, so they rise. So it's the circulation of this middle portion of the Earth, called the mantle, that's believed to have play a strong role in moving the tectonic plates around. Okay, anyway, so that's that. So then the next question is, all right, so the tectonic plates move, but so what's the big deal? The first thing we need to know about the Earth is that there are two types of crust. Two types of crust. Remember, the crust is that outer shell of the Earth that overlies the mantle. And there are two types of crust. One type is called continental crust, and it's generally pretty thick, certainly thicker than oceanic crust, and it's less dense than oceanic crust, which is the other type. So there's the other type of crust, oceanic crust, which is thinner and more dense. All right, so the long and the short of it is that the reason we care about that is, you can imagine if you float something in water, the denser it is, the lower it's going to sink in the water, and the less dense it is, the higher it's going to ride in the water. And since oceanic crust is more dense, it's going to sort of sink lower into the mantle. The crust and the mantle are both solids, but the mantle is sort of ductile. It's kind of plasticky, the mantle. Here's the mantle, and here's the crust up here. And so the denser the crust is, the more it wants to sort of bob down. That would be oceanic crust. So when we think of continental crust, we think of something that's very thick, and oceanic crust, something that's thinner. And so if we were to do a cross section, sort of a vertical slice through an ocean, what we would see is a continent over here, which is underlain by continental crust, and another continent over here, which is also underlain by continental crust, and an ocean in the middle, which is underlain by oceanic crust. And it would look something like that. This is the oceanic crust is thin and it's kind of sagged down. This is the continental crust, which is thick and a little riding up a little bit higher. Now, why is oceanic crust called oceanic crust? And why is continental crust called continental crust? Well, if you imagine taking a giant vacuum cleaner and just sucking all of the water off the surface of the Earth and holding it up in space and looking down at the Earth, what you'd see is that there are places on Earth where the land seems to be kind of depressed, kind of low, and parts of the Earth where the land seems to be higher in elevation. Now, obviously, the light, thick continental crust is going to form the high elevation parts, and the thin, dense crust is going to form the low spots. So when you release all the water out of space and it goes flooding back down to the Earth, it's going to rush in these torrents all over the place until it settles in the low spots. The vast majority of water on Earth is the oceans, and that's going to settle on these big, depressed low spots, which are underlain by oceanic crust, hence the name, oceanic crust. The oceans sit on top of oceanic crust. The continents rest on continental crust. All right, so there are two types of crust, but you can have multiple kinds of crust on individual tectonic plates. And in order to understand how that works, we need to understand a little bit about the way the tectonic plates move. So there are basically two possibilities, and you can see that if you put, there's a vertical slice again. There's tectonic plate A and tectonic plate B, and there's a tree to show you which direction is up, right? So what are the three possible ways that these two tectonic plates, which are touching each other, can move with respect to one another? They can go towards each other like this, in which case you're probably going to get some sort of mountain belt forming as the two collide. You could have them sort of moving in and out of the page. Imagine this is coming out of the page at you, and this one's going into the page, and they're just sliding past each other. That would be an example of, or an example of that would be something like the San Andreas Fault in California, which is where the Pacific tectonic plate and the North American plate just slide past each other. Again, there's a tree. And then the third possibility is when you have tectonic plates that are actually pulling apart from each other. And for reasons we'll talk about in a second, when you have tectonic plates pulling apart from each other, that's where you get oceans. Okay, so let's talk a little bit about this case here where tectonic plates collide. How is it possible that tectonic plates collide with one another? Well, when if the tectonic plates are moving more or less randomly with respect to each other, sometimes they're going to collide, right? And what happens, and this is called collision, what happens when two tectonic plates collide depends on the kind of crust that makes up those tectonic plates. So what happens if you have a big continental crust, chunk of continental crust is one plate, and the other tectonic plate is oceanic crust? So this tectonic plate's moving this way, this tectonic plate's moving this way, and they collide. Well, what we've observed to happen is that the continental crust rides over the oceanic crust in a process called subduction. And you get something that looks like this. So this oceanic crust is being shoved down inside the Earth in a process called subduction. And eventually what's going to happen as it goes down further and further into the Earth is it's going to be heated up, and eventually it's going to melt, and eventually it's going to get recycled back into the crust for ways that we'll see in a minute. But that's what happens when when you have collision of continental crust and oceanic crust. What if you have oceanic crust and another tectonic plate made of oceanic crust? So this is going this way, and this is going this way. Well, again, what we've observed to happen is one of them will subduct underneath the other. And you might say, well, which one's going to subduct underneath the other? And it turns out that in general, the one that wants to subduct underneath the other one is the denser one. Which one will be denser? Well, the one generally that is oldest, for reasons we'll talk about in a second, the older the crust is, generally the colder it is, and if it's colder, it's denser. And so that will be the one to subduct. So let's say that's the older and therefore denser piece of crust would be the one to subduct underneath the newer and younger one. And then there's a third possibility here, right, for collision in plate tectonics. And that is, what if you have two tectonic plates colliding with each other, and both of them are made of continental crust? So continental crust is going this way, and continental crust is going this way. What happens? Well, the first thing you have to wonder is, how could two pieces of continental crust come together? And actually what's happening is they're being pulled together through the process of subduction. So this is a little bit of an unfair diagram. What if we were to draw the diagram more like this? Let's go back and have oceanic crust subducting. Again, there's up, right? There's a tree. Continental crust and oceanic crust, so that the oceanic crust is subducting underneath the continental crust. But if we follow this back, what happens if this oceanic crust is connected to another piece of continental crust? Now, as this oceanic crust subducts, it's going to draw this continent in until eventually they're in a situation that looks like this. Okay, so back to this. So now we have these two big chunks of thick, not very dense, kind of buoyant chunks of continental crust, and neither one of them is capable of being subducted. They're just too thick and too buoyant to do that. And so what happens then essentially is you get sort of this is a dramatically incorrect and oversimplified version of what's happening, but you can think of it like two trains going in opposite directions on the same track. They smash into each other, and you get big mountain ranges, and the Himalayas are an example of that, a modern day example. So are the Appalachians, so are the Urals, and so forth. Lots of mountains around the world. The Alps formed when two chunks of continental crust collided with each other. Okay, I'm going to stop there.